time we noticed that if I have a vector, for example, like this one, this one's called a column vector. If I have a column vector where when a matrix is multiplied, it's some multiple of the original vector itself. If something like this happens, we called this vector as an eigenvector and this value as an eigenvalue. So let me write down the general format. Let's call this matrix A. If I have some column vector V, and if I multiply a matrix to the vector V and I get some value times the vector V, in that case we call V an eigenvector of A, and lambda an eigenvalue of A. And we also say V is the eigenvector associated with lambda. That's the definition. Now, last time I just threw this identity and verified that this is indeed true, but I didn't teach you how to get this vector from the given matrix. Okay, so let's do this. First, I'm just going to show you the method, and after that, if you see how the method does work, then I'll try to explain the theory behind it, why that the method works. Okay. So here's the method of finding eigenvalue and eigenvectors. So the first thing that you do is you take the determinant of the matrix, but you subtract the lambda from the diagonal and set it equal to 0. So subtract lambda from the diagonal and set determinant equal to 0. That's the first step. By the way, when you have a matrix, the diagonal of a matrix always is this diagonal. Okay? See, if you have a square, there are two diagonals, right? For matrices, we only call this one as the diagonal because this diagonal happens to be much, much more important than the other diagonal. Okay? So much important that often when people really, really need to talk about this diagonal, they call it the anti-diagonal. All right? So just keep in mind, diagonal of a matrix is always this way. Right? Okay, let's see what that gives us. Remember how to do the determinant, right? It's AD minus BC, so 1 minus lambda times 3 minus lambda minus 2 times 4 equal to 0. Let's see, this is lambda squared. If I FOIL this out, you're going to see that's lambda squared minus 4 lambda minus 3, actually plus 3, minus 8 equal to 0, and therefore you get lambda squared minus 4 lambda minus 5 equal to 0, and then you get lambda minus 5, lambda plus 1 equal to 0, you get lambda equals to 5. Okay. So that's step one. Step one. And what you get from this step one is that you get the eigenvalues. The solution of these will turn out to be the eigenvalues. Why? That's the part that I'm not explaining at this point. I'm just showing you the method. And after I show you the method, I'll explain to you why such a method will tell you the eigenvalue. Right? Okay. Now step two. Now each of these eigenvalues will have an associated eigenvector. Okay? Every eigenvector that you see, and every eigenvalue that you get, will have an associated eigenvector. Okay? So you have to plug that value back in here because we found out the value, right? And you just have to figure out what V tells you that satisfies this. Okay. So, I mean, one way to do it is plug in 5 here and put this matrix here and set V as A comma B, and you solve for A and B. That's one way to do it. But let me show you a slightly different way, the more efficient way, which is to take this one and plug lambda back in and look for null vectors. So if I plug in, say, for 5, if I plug the 5 back in, what do I get? I get negative 4, 2, 4, negative 2. I get that vector, right? And that matrix. And then the null vector is a vector A comma B, whose resulting product is 0, 0. Some people say vector in the null space, okay. Null space of this matrix. That's the thing I want to know. Now, it will turn out that it's always the case that when these eigenvalues are obtained and you plug it back in, you're going to get two equations which are the same thing. Let me explain what that means. So, look, how do you multiply matrices again?
Across and down.
Across and down, right? So you do across and down. So what does that give you? Negative 4 times A plus 2B. Same thing, you do across down, 4 times A minus 2B. That's the result of the multiplication of these two matrices on the left side, and I'm trying to say this is equal to 0, 0. And the comment that I just made before doing this was that this equation always gives you first element equal to first element, second element gives you equal to the second element, so it gives you two equations, right? You get negative 4A plus 2B equal to 0, and 4A plus minus 2B equal to 0. You get two equations, and it will always turn out that you have two of the same thing, basically. Why are these equations basically the same thing?
Multiply 1 by negative 1.
Yeah, you take the second one and multiply by negative 1, you get the same thing as the first one. Isn't that right? Yeah. So that means that this is a tip. Although you want to find a pair of numbers that which satisfies this equation, you just have to figure out pair of numbers that will make this times this equal to 0. That's all, and you can just completely ignore the second line. That's assuming that you did get the value correctly. If it turns out that the second one is not the same as the first one, that means you probably made a mistake here. Okay. All right. So we agree that the second one is the same thing as the first one. And now just pick two numbers that will satisfy this. Can you give me two numbers that will satisfy this? 1 and 2. Okay, so that's good. So I get 1, 2. Okay.
This is the same thing.
Now, notice that you could also have done 2 and 4, or 3 and 6. That means for one value of eigenvalue, you can have infinitely many eigenvectors, but they're all multiples of each other. Okay? And that's why we say n. Sorry. I should really say V is an eigenvector associated with lambda. So that among the many things, you just find one that's non-zero. Okay? So the only requirement for the eigenvector is that V cannot be the zero vector. And any multiple of this could be chosen as the eigenvector, but we tend to find the simplest integer one if possible. Sometimes it's impossible, so yes?
Could 0 be an eigenvalue for?
0 could be an eigenvalue. In that case, you will still have some so lambda could be 0. That's okay, but V is not allowed to be 0. Okay, that was a good question. Thank you. All right, so that's the eigen. So this is eigenvector for lambda equal to 5, right? Now, what if and you have to do for both. Now, for lambda equal to -1, what do you get? Let's see. You have to plug in -1 back in there. So if I have 1 minus -1, 2, right? 2, 4, 3 minus -1 is 4. A, B equal to 0, 0, right? And you only do the top across down, so you get 2A plus 2B equals to 0. Give me two pair of numbers. Two numbers. Huh?
They just don't have to be the same number, right?
Yeah, I don't need to do the bottom because it's the same thing. I only need to do the top.
1 and -1.
Yeah, 1 and -1. So for this one, I got 1, -1. And that's it. We say, so the result is has eigenvalue 5 with eigenvector 1, 2, and eigenvalue -1 with eigenvector 1, -1. And this is the result, which actually verifies that this is indeed true. How would you verify that this is true? How would you? So it's basically these two steps, but how would you verify your answer is true? You just see if it does satisfy A, V equal to lambda V. If this is true, then you're right, right? So if I have 5 as lambda and 1 and 2 as your vector, this is what we're claiming, right? 1, 2, 3, 4, and then 1, 2. If I do this calculation, they must better be equal, right? And they are. If you multiply these two, 1 times 1, 2 times 2, add them up, you get 5, so it's equal to 5, right? Across down, you get 4 times 1, 3 times 2, that's 4 plus 6, which is 10. 5 times 2 is 10. So they do work, okay? So those are the steps that you take in order to get the eigenvectors and eigenvalues.